So thanks everybody for joining us for the second keynote of our first day of JuliaCon. It's going to be presented by Dr. Michael Herbst and Dr. Rachel Kurchin on the topic of quantum chemistry. Obviously, they know a lot more about their keynote than I do, so I'll let them take it away in a second. Just another quick reminder that we'll have the closing ceremony after this and a poster session also at the end of this keynote. And with that, take it away.
Thanks so much, Katie. We're both really thrilled to be here and really honored to be giving what I'm given to understand is the first joint JuliaCon keynote, so hopefully this all logistically goes off without a hitch. And I also want to lead off by saying that we're definitely here representing a much broader community, some of the members of which I see in the audience, and some are maybe listening in online. And we'll shout out several folks by name throughout the talk, but I wanted to kind of lead off by thanking all of the folks who've been involved in the various JuliaMolSim packages and the sort of broader Julia for materials ecosystem. And so with that, I'm really excited to tell you all a bit about materials modeling and how we can build bonds across atoms, code, and people. So I want to start, since this is not a material science audience, by saying a little bit about what is material science and engineering. So I myself am in a material science and engineering, or MSE, department. And the kind of things that we think about really hinge on this nice sort of chain link figure that I have right here. And it's fundamentally about understanding on the scientific side and leveraging on the engineering side relationships between these kind of key attributes of materials. And so we can think about at the starting point, processing. So what do we do to a material? How do we make it to be in some particular chemical formula, some particular structure? You know, it could involve various treatments and under different conditions. And these things all in turn affect the structure of that material. And another kind of key signature of MSE is that we think at a bunch of different length scales. So from the atomistic length scale, how are these atoms arranged? Are they ordered? Are they not so ordered? All the way up to, through sort of mesoscale, up through kind of macro scale at the scale of something that, we could hold or touch. And it's this structure that in turn dictates the properties of the material. So physical things that we can measure related to it. For example, the melting point, perhaps, or how well it transports heat or electricity or some other form of energy. And those properties then are pivotal in determining the performance of that material in some sort of application that we might then want to use it for. And so I want to motivate this. We're here in the Netherlands, and hopefully many of us are also cheese lovers. So I'll motivate this as a concrete example by talking through it in the context of cheese. So if we start from the end of processing, we start with milk from sheep, goat, cow, whatever. There's a bunch of processing that goes into it. Maybe we're mixing together different things. Perhaps we're adding something. There's often an aging process that might have to happen at certain conditions of temperature or pressure or other sorts of atmospheric conditions. And all of these things ultimately, in some form or fashion, determine the structure of that cheese that we get. And we can, again, think about this at these many, many different length scales. So on the left here, I'm showing a single casein molecule. This is one of the very important molecules that's found in milk. Casein does a really interesting thing. It forms these spherical micelle structures, and that's what I've shown in the middle here. Those micelles, in turn, will aggregate to form what we call cheese curds. And so I'm showing a microscopic image of a cheese curd on the right, and exactly how we process, what the inputs to this processing are and how the processing proceeds all determine the details of this structure. What different, allomorphs of casein are in there, and all sorts of other interesting things. Of course, this then determines the properties that we can measure. So we might think about mechanical properties, like how stretchy the cheese is, or what it's, how does it melt, at what temperature does it melt. We might think about other properties, perhaps olfactory properties that some of us might like or not like so much. But again, ultimately, all of these things combine to determine the performance of the cheese. How pleasant is it to eat? Does it have a nice texture? Does it have a nice taste? Hopefully we all enjoy, we might not call it this, but in some form, evaluating the performance of cheese, right? And so I've gone through this, and hopefully it gives you a sense, especially if you're not a material scientist, of the kinds of things that material scientists think about in a kind of relatable context. But if we think about the academic practice of material science, I'm sure there are some material scientists somewhere who talk about cheese, but many of us think about other things as well. And what do we mean by a material? So what's kind of the scope of this here? Basically, we're usually talking about something that's solid or solid-ish. Usually the sort of fully liquid or gaseous things, we typically leave that to the purview of the chemical engineers. There's lots of really interesting and important stuff there, but the scope of materials science is typically sort of solid or maybe like slightly squishy or goopy things. This includes a lot of different things. We typically think about 4 main materials classes: metals, ceramics, polymers, and then composites, which can be mixtures of those. They can exist in a lot of different kinds of states or phases. They might be atomically ordered or not so much. They might exist in different geometrical form factors, nanocrystals, thin films, bulk chunks of material. I've shown some representative examples at the bottom here. So wood is a really fascinating biocomposite material. We can think about coins. That's a classic type of metal that many of us maybe not so much anymore interact with, but certainly once upon a time probably did. Plastics we see all over our daily lives, the chairs that you're all sitting on, oftentimes drinking straws, all of these sorts of things. So we all interact every day with materials of many different kinds. And materials are also important to many aspects of technology and sort of moving the world forward. It's an extremely interdisciplinary field, so MSc relies and builds on concepts from physics, chemistry, engineering fields, as well as the biosciences. I mentioned wood and other sort of biomaterials as well before. It's extremely interdisciplinary. It's something I personally really love about the field. You get people with all sorts of different kinds of disciplinary trainings, and it often takes people from all those different backgrounds to really successfully tackle a problem. And these new and improved materials, we have solutions to many of the, we have existing solutions to many of the problems of this century. Whether it's the climate crisis or access to clean water to improve global health, many other things. In many cases, the performance of those solutions and whether or not they're good enough is fundamentally materials limited. And so new materials have the potential to kind of unlock better, more efficient, more economical solutions to these problems. And that's a big motivating factor, certainly of my research personally, and I think of the research of many folks who pursue materials for a whole wide variety of applications. So recognizing that we're at JuliaCon and kind of pivoting now from the extremely general introduction to material science into the computational aspects specifically. When I talk about computational material science, this is still a really broad term, right? So what we mean here in the most general sense is that we're modeling materials on a computer by using that computer to solve some set of governing equations that we believe that we can use to model that material or to describe that material. These so-called computational experiments can really offer valuable complementarity to lab experiments or to pencil and paper theory. We can often access length scales in a simulation that we can't necessarily see or measure in a lab. We can simulate systems that are far more complex on a computer than we could ever do with pencil and paper. So it sort of fills this nice niche in between. Often you'll hear folks refer to computational science generally as kind of the third paradigm of science. So you had sort of the empiricism governed by experiment and theory and computation, and now you start to hear talk of kind of the fourth paradigm of sort of data-driven, ML and AI, and we'll talk a little bit more about that later on in the talk as well. This is really becoming integral to a lot of aspects of material science and has the potential to really transform what we can do or the scope of scale of what we can do. And relatedly, computational MSc in particular offers tremendous value for acceleration of that sort of materials design, discovery, and optimization process that I was alluding to on the previous slide that can be important for advancing technological solutions to all manner of societal challenges. So I'm going to get a little bit more specific now and talk about a few aspects of computational materials science organized on this plot here. And I'll preface this by saying, this is going to be a pretty high level and broad introduction, and I'm an expert in particular areas that I'm an expert in. If you are a computational materials scientist, first of all, if we don't already know you, come introduce yourself, because we want to meet more material scientists who are using Julia. But also, if I somewhat misrepresent anything that you particularly work on, I apologize in advance for that. Feel free to correct us or add something during the Q&A if you'd like. And so what I'm talking about here, when we're on these two axes here, we have the length scale on the horizontal axis. So this is what length scale of materials can we access or describe, ranging from nanometers or even angstroms all the way up to multiple meters, and similarly timescales from picoseconds up to seconds. And I'll note here that the timescale we're talking about is the physical timescale in the material. This is distinct from the runtime of the simulations, which will generally be many orders of magnitude longer. Certainly at the lower timescales, the runtimes of the simulations will be many orders of magnitude longer in general than the timescales that we're simulating. So that's an important distinction to make here. And so I have kind of four broad buckets of types of simulation that I'll go through briefly, and also include a little bit of, for those of you who are not already interested in these aspects, a few kind of motivating concepts of where ideas from math or numerics or CS come in and have really a lot to contribute and add a lot of richness to why these are sort of interesting, challenging, multidisciplinary problems. So starting from where I think both Michael and I spend most of our time thinking about with electronic structure, so this is again at those shortest length scales and time scales, ranging up to maybe a few tens of nanometers perhaps, and then kind of up to maybe the nanoseconds in terms of time scales of processes that we can think about. We're typically thinking about order of 1 to maybe a few thousand atoms, so a very, very small number of atoms that we're thinking about. The core governing law, their governing equation, is the Schrödinger equation, so we're thinking about the wave functions or some approximation thereto of the electrons in these materials. There's a number of existing Julia packages designed for this, one of course being the density functional toolkit that Michael is a developer on, as well as Fermi, and a bunch of really fun math concepts come in here as well. So the Schrödinger equation is a nonlinear complex eigenvalue problem, and there's a bunch of interesting and often quite bespoke numerical methods that go into solving that in the kind of regimes that we're thinking about, which I've kind of summarized here. Moving up sort of one rung on this sort of length scale and time scale, we can think about molecular dynamics. And so here we're still resolving individual atoms or molecules. We're from maybe the hundreds to at the sort of most heroic scales, perhaps of the order of 10 to the 13 atoms. Here, we're no longer thinking about quantum effects and electronic interactions, but rather the governing law is now Newtonian mechanics. So if you remember just F equals ma from a high school physics class, we're basically just running that many, many times on many, many particles to simulate their motion. I see Joe is in the audience right here. Joe Greener is the developer of Molly, which is the main Julia package certainly that I know of for doing MD simulations. And again, a ton of really fun, broader math, numerics, CS topics. So we're fundamentally solving a massive system of coupled ODEs, and we need to do that in particular with symplectic integration in order to conserve energy. So there's a lot of fun numerical methods that come in there. When you're thinking about simulating under different particular thermodynamic conditions, there's lots of interesting control schemes and constrained optimization problems that come in. When you think about how to parameterize the various potentials that we use in actually computing these forces, a lot of other interesting stuff comes in. So now we're verging into the territory where I'm certainly less of an expert, but I think it's important to mention as well. So at the sort of mesoscale, now we're no longer resolving individual atoms, but we are sort of solving equations that somehow are aware of the existence of atoms, let's say. So we can think about reaction diffusion or various phase field laws, the Boltzmann transport equation. And I'm not actually aware of a Julia package that's a specialized package for these types of problems. That being said, however, these are all generally partial differential equations. So any of the numerous wonderful tools that are capable of handling partial differential equations are certainly a good place to start for this. As in many different fields, with materials, there's certainly specific things, and one could imagine making a sort of specialized package that builds on those things. But not currently aware of one. Feel free to correct me if I'm wrong. And then finally, up at the longest length scale and physical time scale, we can think about continuum modeling. So now think about finite element or finite volume approaches, and the governing laws here are basically various continuum descriptions of matter, which depending on the problem of interest might include mechanics, electrostatics, transport of various quantities. Those are often coupled together in various ways. We might need to explicitly impose thermodynamic constraints because those are no longer going to be emergent if we're not explicitly resolving particles. There's a number of packages that are well suited to doing this in Julia. And again, a bunch of fun math ideas that they build on as well. OK, so having sort of given that basic setting, and hopefully even for those of you who may not be materials scientists, convinced you that this is somewhat interesting and has some interesting technical meat to it, we'll come back to this kind of chain link thing. So you can now maybe see that if we think about materials science, we're kind of going up the chain in a way, understanding how processing affects structure, and in turn, how that dictates properties. From the engineering side, we often want to go the other way around. So we're interested in designing or discovering a better material for some sort of application. We ultimately want improved performance, and that necessitates the improvement of particular properties that we may know or suspect to be limiting that performance. So we'd like to be able to design materials kind of going this other way around. And computation here has a really key enabling role to play in that process because it enables us to save a tremendous amount of time, money, and energy compared to experimentally screening many candidates in the lab. And just to give you kind of a sense of scale on the energy piece here, one fume hood, which would typically be one very small part of an experimental lab. A lab may have multiple fume hoods, a lot of other large and energy-consuming equipment. Just that one fume hood has a typical energy usage on the scale of 2 to 3 average households. So this is expensive, as I mentioned, in terms of time, money, and energy. And we want to use those resources as efficiently as we can. And if we can use computation to kind of pre-screen, then that becomes really valuable. So let's talk about what the actual sorts of computations we're doing are in a little bit more detail. So if we're thinking about going to, again, back to the bottom of that sort of length scale and time scale, if we're thinking about doing an electronic structure calculation, perhaps as I spent much of my PhD doing, trying to identify promising materials for solar cells, we would basically set up the sort of unit cell, the crystalline repeating unit in that material, use something like DFTK to solve Schrödinger's equation for those electrons and interrogate the results of that in order to compute certain properties that we might know are important related to light absorption, charge transport, various important things in these materials. And this can give us a sense of the material's suitability. And I'll say a little bit more detail about that in a moment. But the key point here is that this one calculation is of a sort of modest to moderate computational cost. It would run on the order, depending on the size of the material and how detailed a calculation you want to do, it could run on anywhere from a handful to maybe a few tens of cores. And we usually run these things on supercomputers not because we don't have local machines that have access to that many that scale of resource, but because we fundamentally want to do this at a very large scale so that we can screen many, many, many materials. So we can automate this process by screen many different structures, many different chemistries, different sorts of materials in this kind of embarrassingly parallel way, at least at one pass here, right? And this is the kind of HPC we're doing. So it's a little bit of a different, a lot of times people talk about HPC. I think it was Valentin who was earlier talking about a Gordon Bell attempt. These are like basically single jobs that take up an entire supercomputer. That's not really the regime that we're in. We're talking about sort of single to couple of node jobs, and we run many, many, many of them. So that's the sort of scale of HPC, the form of HPC that we're in. And a typical kind of workflow here in a computational materials discovery context, we often have these sort of funnel graphics. So we might start with a large list of candidates drawn from some online database. There's many and more every day, kind of wonderful online databases of different sorts of materials. And we start with sort of the lowest cost filter. So whatever the cheapest thing we can compute is, we use that to eliminate some candidates. And then we sort of apply progressively more expensive computational screens on the remaining ones until at the end we hopefully have like an experimentally tractable number of materials candidates that we can hand off to our experimental colleagues, and hopefully they have a decent chance of a good hit rate at finding something that's interesting or promising for whatever application we're thinking about. So this is a typical kind of workflow or paradigm that these things will be set up for. And it's worth noting that these types of calculations, MD, DFT, other types of quantum simulation, already take up a noteworthy share of the world's supercomputing resources. So as one example, on Archer 2, which is a machine that we have the capacity to get data for, you can see that in the blue here, these things are routinely taking up of the order of half of the resources of that particular supercomputer. And another thing I want to highlight is that this approach, and computational MSE more broadly as just this kind of set of techniques, whether or not it's specifically used in this high throughput way, is used extensively in industrial contexts as well as academia. So this is an extremely non-exhaustive list of companies that I'm aware of that do some form of computational materials science work. And so this is quite pervasive in a number of different industries and types and scales of companies. So this is a thing that is out there that folks in this audience may or may not have been aware of previously. So with that, I'm going to hand it off to Michael to start making things a little bit more concrete and a little bit more Julia specific.
Yeah, thank you very much, Rachel. So I'm indeed going to talk about how to actually compute complex properties. And the guiding example that I have in my head is two things. So for example, here, if I want to compute a melting point of gold, so this is gold which is melting, or for example, if I want to understand how ions actually move in a lithium-ion battery, then what I'm after is dynamics. So I want to understand how these things move around here. And just to make it a bit more concrete and to get it to a scale which is sort of doable on the sort of simple HPC systems that I have in my lab, I'm looking here at a lump of aluminium, right? So this is just a lump of aluminium, and I'm interested in, as you see, simulating here the thermal motion of the aluminium as it sort of, just naturally vibrates a little bit. And this dynamics is really important, indeed, to just from sort of analyzing the so-called trajectories that come out of such a simulation, we can indeed understand like the melting point of aluminium, or for example, how like a lithium ion could transport through the aluminium, okay? So that's the sort of setup I have in mind. And how do we do this basically in a step-to-step guided fashion? So one time step, so sort of one frame that you saw in this video would be that you start from some structure. You do indeed invoke something like this density functional theory, this lower left tier of computation that Rachel has been talking about. And then you get the energy E here and some derivative of the energy with respect to the positions, this grad E, the forces. And with this, indeed, you solve Newton's equation, and then you propagate a little bit the structures, and so things change, and you really have done some motion, right? So we do this in the video for 1,000 time steps, and as Rachel has already mentioned, really doing this for 1,000 steps using the sort of the standard, the most accurate theory, one single time step takes on the order of hours, right? So 1,000 times 1 hour, let's say, is a considerable amount of time, and I didn't actually spend that much time making the video. So what did I do? And this is where the machine learning comes in. Actually, I didn't use the underlying density functional theory, this high-level method, to do my simulation. Instead, I used a machine learning surrogate. And this surrogate can be evaluated in typically under a second, right? So now I'm all of a sudden in the regime where I can actually do something reasonable, like making up such a nice video that you saw here. But then, of course, this raises the next question: how do I actually get the surrogate? Okay. So, of course, the general idea for surrogate modeling is you generate some data. So in this case, data generation actually, again, invokes a lot of computation, right? So we are still in this HPC regime that we have been talking about, that we need to run maybe tens of thousands of data generation steps. And then in the end, I can sort of, maybe do a linear system solve or something. And then I get my trained machine learning model. And that I can then replace by the actual DFT computation. Now, the thing here is, though, which model should I choose, right? Even on the machine learning model side, there's really plenty of them to choose and to try. And just to give you some ideas, the typical questions people ask is, how expressive is my model? Meaning, like, can I actually even represent all the physics that I'm interested in? How accurate is it, right? Like, how much does it actually reproduce the high-scale wave function system, the wave function method that I have been using? And then, of course, data requirements, right? Some machine learning models, I do maybe 1,000 calculations, I'm done. But for others, like neural networks in particular, I might need much more data, meaning that I actually have the cost of generating this data, right? So there's really a lot of considerations to take into account. And the point really I want to get across here is there's no one size fits all. And so the flexibility to in your workflows, swap this out, swap this in, play a little bit with the different machine learning models. This is really something that we need in order to make progress in this kind of research field. Now let's talk about how this looks in practice. So this is just some input files. So actually many codes in this field still use text-based input and output. And this is some standard input files that people would traditionally use to run these kind of calculations, this aluminium simulation that you've seen. And just even by looking at the parts that are highlighted, you see the structure and the formatting is very different. So every code has sort of their syntax, and in particular, this is not very well standardized and changes sometimes between versions, okay? So you can imagine what kind of a nightmare it is to sort of flexibly, or rather non-flexibly, swap in and out different codes. So what's the solution? Of course, the idea is to invoke the power of abstraction and to say, well, I mean, some structure sort of is some abstract object I do want to somehow represent, and some, calculation object that just uses the structure and gives me back some energy and some force. That's also some standardized object that I can somehow abstract, right? So let's just do that. Now, that's exactly sort of what we have done in the ecosystem. And in fact, we are now at this point where this aluminium video that I showed you earlier has indeed been completely generated using Julia tools. So with this script here, I use DFTK to generate the underlying DFT data. Then with the second script, I use this package called ACE Suite. So ACE is one kind of machine learning model that is used in the field. I fitted such a ACE potential, as they say. So basically, I fitted such a surrogate for the DFT calculation. And then I used Molly to run the calculation and eventually produce the video that you saw. So the point here is that we already pass the structures around as abstract systems, so I don't really have to worry about, changing units or converting things between the conventions that the different codes are using. Of course, I also, well, that's at least the plan in the near future, to also use really calculations, abstract calculator objects, as we call them, to swap in and out the kind of, computations that is underlying for example, the dynamics here. Okay, I mean, this sounds like an obvious thing to do, and indeed we have not really been the first to do this. So in the ecosystem, in the material science and computational material science ecosystem, there's really a number of people that have worked on this kind of idea of abstraction. The one that has guided our thoughts most is the so-called atomistic simulation environment. And indeed, the point I want to get across here is that these codes exist and they work reasonably well in practice, but there are some issues. Like, for example, in fact, they're usually just wrappers around this text-based I/O. So they just drop an input file, they run the computation, they pass the output. Okay? And this actually means that whenever I want to get a new calculator working, meaning I want to try a new model or some new idea, actually this is non-trivial. I always have to write this parser and I always have to write this generator for the input. There's sort of usually not a standardized API. And it's actually not just a 2-language problem, it's typically even a 3 or 4-language problem, right? So I can have some Python part that is actually the workflow management system. Then I sometimes have like a Fortran part that is wrapped via C to something else. And I mean, this is really a bit of a mess. And that actually means really also the amount of effort people have to put in to be able to really write these calculators, right? This is really, a PhD first has to understand all these languages. So this is really not in line with the opportunities and strengths of Julia, clearly, and basically it's not so able to export some of the flagship features that I'm going to present to you in the next slide that Julia is really able to do. And so this is our motivation to sort of try to give a Julia-based approach to overall this whole material science and ecosystem abstraction problem. So now let's talk about some things that Julia tools can do right now, which are in fact actually not so easy to do in some other standard tools. So one aspect I want to get into is inverse design. So let's say you actually have such a whole simulation that I showed you, like these 1,000 time steps, and now you're asking yourself the question, I know that aluminium has this and that melting point, okay? Can I actually train my machine learning model such that it reproduces the melting point? Okay, so I'm not what is traditionally done, I'm not using so-called proxy quantities, right? So I'm not just using the machine learning model, I'm not training it to reproduce the energies and forces, but I'm actually training it to directly reproduce the physical observable. So this is actually really tricky, and it's hardly done in practice, because it's actually a typical case where you want to do end-to-end algorithmic differentiation, right? In the end, you somehow want to have a loss function, and you want to backflow your gradients until you can update your machine learning parameters. And this is, however, something that needs to be exposed. And traditional interfaces, in particular when you think about file I/O, it's really tricky to do these things. Now, Joe has indeed actually done this, and so this is one of the cases where Julia is really like pushing the state of the art, and of course that's something in our implementation that we want to keep. Some other examples now from the people of the ACE suite is that something called as active learning. So the idea here is that if we train such a machine learning model, it only knows something about the structures or the vicinity of the structures that we gave it. So if it's somehow not confident, meaning that we're not really able for a particular structure to reproduce the exact energy and forces, then we need to run additional underlying data generation steps. So what does this mean from the point of view of a workflow? Well, it means that while you're actually running your simulation, like producing this nice aluminium video, you're always changing between running the high-level ground truth, running the machine learning model, running the dynamics, updating your machine learning model with extra data, and so on and so forth, right? So it's not just a simple linear workflow, but it's really starting to become a more complex and much more involved procedure. And this is something we would like to do. The other thing we would like to do in DFTK, we've worked actually quite a lot to come up with more robust algorithms, which we want to test, of course, in practice, but also we came up with ways to quantify errors. So this is a band structure, a really important quantity in material science, and we are actually able, in some settings, to predict the error that the numerical procedure makes. Now, of course, this kind of error we would like to use in our simulation. Or similarly, what we worked on in DFTK is being able to forward diff and compute sensitivities, again, of quantities of interest. So again, the same idea is if we have all of these sensitivities and we have all of these gradients, can we use this in our simulation? Can we propagate this forward? Right? So this is essentially something where we again need to augment our workflow. And here's going to be a talk by Niklas, actually on Thursday, who's going to talk a bit about some issues of AD in the context of DFT, because actually it's not as simple as I make it sound here, but anyway. But the point is we want to exploit these things, right? We have it now and we want to exploit it. So essentially this leads to a shopping bag that we came up with when we were starting to design this interface of abstract system and basically atoms calculator. So in the end, we really want to improve the composability, right? So all of these tools are out there. I showed you some flagship examples, but actually what's definitely missing is good integration between them, right? Really exploiting this in a holistic way. And being able to use error control, these new machine learning models and AD in a whole Julia workflow from front to back. Then, of course, the next problem is that in this field, there's thousands of methods. We will not be able to implement thousands of methods in Julia within the amount of time and energy and people that we have. So we really need a two-way communication with existing tools. And that's not just necessary for us to sort of test what we're doing, but it's also important for adoption, because people need these different methods. They need this whole selection of methods to be able to do the physics and the chemistry they want to do in practice. Next question is, I talked about active learning, I talked about on-the-fly data generation. This leads to a problem which I would call dynamic and heterogeneous modeling, okay? So the issue is, if you think about like an active learning pipeline, what happens is that in the beginning, you need to run a lot of ground truth density functional theory simulations. That typically works well on CPUs. But then, as you're basically training your surrogate, this is something you do on the GPU. As you're sort of using your surrogate more and more, and you're using less of the DFT, the balance between running CPU and GPU is dynamically changing throughout your simulation. Somehow you need to dynamically schedule these jobs on a big cluster, right? We talked about tens of thousands of jobs. Somehow this needs to work. This is not so trivial. And then the next question is, of course, how can we integrate across communities, right? So mathematicians, they work really on the hot loops to come up with new algorithms, new ML kernels, and so on. They need to be able to do this without really worrying about all the HPC business. But still, they need to be able to test in practice their algorithms, because some of the algorithms that look nice on paper, they might not actually work. So again, for testing and also for adoption, because people will not use algorithms if they're not push button available in their favorite simulation. And so here I want to quote Alan, people compose of software composers, and I really think this is something where Julia can make a crucial difference. Okay? So with this, I hand back to Rachel. We'll continue.
Yeah, thank you very much, Michael. And so I want to so we've talked a little bit about some of the specific stuff that we've been developing within the purview of JuliaMolSim. So this atoms base, which is meant to be a sort of interface for specifying structures. That's been around for a couple of years. Atoms calculators, which is a bit of a newer effort for these sort of abstract calculator ideas. In the broader Julia materials ecosystem, what can we do today? So you can interact with these abstract systems through a number of packages, including Atoms Builder for building some of these structures, Atoms.io for reading and writing to wide variety of the various standard structure files that are used, structure representation text files that are used in different contexts. Some calculators that are out there. These are not all implementing the Atoms calculators interface yet, although they hopefully will sometime soon. So there's DFTK, of course, and there's an update talk on that on Friday that Michael will be giving. Interatomic potentials, which specifies a variety of potentials for interaction between different particles. ACE suit that was mentioned previously, that's developed by Christoph Ortner and his team at UBC. A number of different active learning tools, and there's some talks coming up later in the week on those as well. One we don't have a bullet point for here, but I think Joe has a Molly talk like right before Michael's on Friday, if I remember correctly. Oh, that's in the next one, sorry. Dynamics. We can do dynamics using these potentials, and Molly is great for that. There's also Vonnier for localization of electronic structures, so that's more in that sort of wave function space, as well as a bunch of packages for integration with external ecosystems. So we mentioned ASE. There's LAMPS, which is one of the major MD codes that's in use in the broader community today. SPGlib for interacting with certain kind of specifications of crystal structures and symmetries. So there's a variety of things out there. They don't all talk to each other yet quite as well as we might like. There's also a bunch of other cool stuff that didn't quite fit into this talk, but we wanted to get a few shout-outs in there. So there's Cell List Map, which is developed by Leandro, and that's what's currently used for neighbor lists in Mali, I believe. Freebird.jl, developed by Robert Wexler's group for implementing these interesting nested sampling approaches for developing phase diagrams. I'll plug some of my own stuff a little bit. So during my postdoc, I worked on both developing new models for kinetics, or basically how fast electrochemical reactions proceed under different kinds of settings. So this is really important to understand. For example, if you want to charge your electric car really quickly, a lot of the models that we have now don't work very well at extremely high reaction rates, high currents. So we developed a model that works a little bit better for that, as well as in some slightly more exotic circumstances, like the twisted trilayer graphene that I'm showing in the figure here. And this is all implemented in a Julia package called electrochemicalkinetics.jl that can makes nice use of multiple dispatch for computing these rates according to different models that allows you to easily compare them. Shout out especially to Daria Gandhi from Julia Hub, who helped with making the AD work nicely with this, so that I can now optimize backwards through these for things like parameter estimation or doing other sorts of introspection to build up these kind of electrochemical phase diagrams, which is what the third paper is here. And of course, other types of simulations that we didn't mention as well. There's a neat package out of Reinhard Maurer's group at Warwick called NQC Dynamics. So this can do these sort of mixed quantum classical dynamics. This figure, I believe, is electron dynamics at metal surfaces, so sort of interesting things that happen at interfaces between different materials. So, and this is also not an exhaustive list. There's a bunch of cool stuff out there, and we're happy to talk more about this and anything else in the Q&A, during the poster session, et cetera, et cetera. Current state of JuliaMolSim, we've alluded to some of this already. To date, as things tend to go in academia, and package development is driven primarily by the research questions that we want to tackle, right? So the ecosystem is sort of co-evolving with the things that we're working on, that we have funding to work on. And as a result, these packages often kind of lack breadth, although they have been becoming more mature recently. And Julia tools, as we've hopefully convinced you, have certainly been a key ingredient in many, many cases to push the state of the art in terms of what's possible. And there's been also some community recognition. So Joe and Michael and myself both all relatively recently started junior faculty positions. And I think this is, of course, great for our own career progression, but I think is a recognition also of Julia and what it's able to help achieve, that it's contributed to that sort of career advancement. Unfortunately, interoperability and collaboration have largely been unfunded side projects thus far. And I think many people are familiar with this kind of quandary. The JuliaMolSim organization has been around for maybe about 5 years. Atoms Base was started after I think it was a BOF that Michael and I ran at JuliaCon in 2021. And then Atoms Calculator started a little bit more recently, just in the past half a year or so. And we've been having somewhat more regular discussions and working to collaborate and build kind of consensus on what these interfaces should look like. But a lot of this is still relatively early stage. I think we're certainly both here extremely optimistic about the potential for Julia in this space, and I think there's a lot more to be realized than what we've shown you today. But this full integration is definitely in early days. And of course, funding is always a challenge, right? If you can get funding, that contributes tremendously to kind of the stability and maintainability of all of these things. And this is an issue that is absolutely not unique to our community. OK, some ongoing projects. So kind of, again, in the same theme, increasing internal interoperability and collaboration. So we've been actually undergoing a pretty substantial redesign of the Atoms-based interface and working to finalize what the interface for Atoms Calculator will look like. Putting these two together will allow us to build geometry optimization. So this is a really common kind of task in atomistic simulation, where you basically start with some initial guess of where all the atoms ought to go, and you want to find what the lowest energy configuration of them is. And so you typically will compute the forces and sort of scooch all the atoms over in the directions of the forces. And this, of course, requires a representation of the structure and a way to compute those energies and forces. And it's nice to be able to swap in and out different representations and methods for those things. So these abstract interfaces combined into this will provide a nice platform for doing that. We've also been talking about a sort of broader redesign of how we do neighbor lists that's more amenable to implementation on different types of hardware, which again will increase this kind of portability and interoperability. And then again, these kind of cross-ecosystem integration pieces. So Michael has been working to integrate DFTK with AIDA, which is a pretty widely used workflow manager for DFT packages, and has really good kind of support and infrastructure for these really high throughput workflows that can have different kinds of complicated interdependencies to them. There's, I believe it's Temu, who's been working on getting Atoms Calculator to work with ASE, this Python-based package we mentioned before, as well as some other things. And generally, the goal here is just to improve testing, improve adoption of these things. A lot of things don't yet necessarily have sort of fully stabilized interfaces or entirely complete testing or documentation, and we're aware of this, and we are working towards it. And plug if you want to join us at the hackathon and try to help with any of that this week, perhaps. And I think another thing that's really important to acknowledge, right, is like, not everything is rosy, right? There's challenges along the way with all of these things, and it's important to be transparent about that. So I'll hand it back off to Michael to summarize some of the gripes and challenges that we've come across along the way here.
Yeah, and I'm going to be quick. So basically, I think the biggest issues on sort of the Julia adoption side are that people perceive Julia as a language that makes overly ambitious promises. So I think it's something where we as a community have to be very careful when we make promises, because if people see them not satisfied, and that can mean just, Julia didn't download properly, that is a problem. So we have to be very careful in documenting and making sure that the promises we make can actually be achieved. Other issues that we have already been talked about in this conference is binary support. I hear that's going to improve. I'm very much looking forward to this. This is a big deal in integrating our code with the other ecosystem that, as I explained to you, is really important and necessary. Then on the JuliaMolSim side, there's sort of the standard stuff of not having all the methods, but there's also things like documentation and performance. So documentation definitely is on us, but performance, I think, is something where I'm sure there's many low-hanging fruits, and if you guys who are probably much better at performance engineering than some of us are, can take a look at some things, this would us as an ecosystem really push forward. Then there's some other things like lack of some utility packages. Again, we're trying to do some of this at the hackathon. Please reach out if you're interested to help. Now, overall, for the shopping list, I think we have made a good start at many things. One thing that we really haven't tackled is dynamic scheduling. And I think, again, this is something where Julia can shine. And so this is something where, again, we would be very interested if you have some ideas and some ways to sort of get started on this topic. All right, so how can you get involved? We already mentioned it a few times. Yeah, try it, right? Try our stuff and tell us what breaks, right? Because I'm sure there will be things breaking. Otherwise, we have a nice Zulip server where you can basically connect with the overall community. And here at JuliaCon, we plan to go and have a nice chat after the poster session. And at the hackathon, as I mentioned, we have some projects, some ideas. Feel free to reach out if you want to help. Particularly if you're a graphics person. We need graphics people. So people who can make nice illustrations and so on. All right, so a bit of advertisement. I have an open postdoc position at the edge of Bayesian inference and learning and inverse materials design. If you're interested in that, there's a link to check out. Then we are going to organize a nice Julia-based workshop here at EPFL towards the end of the year. Some of the people in the audience are already coming. Julia for numerical problems in quantum and solid state. And Rachel is also doing something.
Yeah, so I also am organizing a workshop that'll be at my campus at Carnegie Mellon in Pittsburgh. It's funded through the Molecular Sciences Software Institute, which is a really awesome organization out of Virginia Tech. And that's going to be basically on the same topic of what this keynote was about, Julia for computational, molecular, and material science. That's going to happen towards the end of October. We don't quite have a registration page up yet, but if you hit that QR code, which we're happy to go back to, that'll put you on our Zulip, and I'll be posting details there as soon as we have them. So we'd love to see you there if you're interested in playing around with this stuff, and we're really hoping to attract folks from the Julia, from the JuliaMolSim community, of course, but also from the Julia and not material science community, as well as from the material science but not Julia community. So kind of bringing all these people together to really talk about, best practices, potential pitfalls to avoid, and all of these things as we continue working towards making this ecosystem more mature. OK, so to kind of wrap things up, I won't read every word on this slide, but sort of to give you a kind of summing up of what we've talked about. Hopefully, we've convinced you that computational material science is interesting and has interesting problems for people, even those who are not specifically interested in material science or physics or chemistry. There's a lot of interesting computational problems, like the importance of these dynamic and heterogeneous workflows that Michael was telling us about. The JuliaMolSim ecosystem is something that we're really excited about pushing forward. It's relatively early days. There's a lot of things that have a lot of maturity building to do, but I'm certainly extremely optimistic about the potential for Julia and for these tools to contribute to this field in the future. And of course, that doesn't mean that there aren't other challenges moving forward, both on the sort of human side as well as on the technical side. And we're excited to kind of keep charging forward and addressing those and improving all of these tools. So with that, I'll acknowledge this is a very, very limited list of folks. On the left, folks who've been really involved in the Adams Base and Adams Calculators efforts, particularly in some detailed conversations that have happened over the last several months leading up to this, putting together the little demo that we showed, and all of that. And of course, both Michael's research group, my research group, and I want to particularly shout out the SESMICS team at MIT. And then, of course, various institutions and funding sources that have supported both Michael's and my groups and our research more broadly. And with that, I will put up all of these various ways that you can reach us. And I think we do have a bit of time left for questions, so we'd be happy to entertain some questions. Thanks so much.
Questions? You mentioned fairly simple-sounding properties like melting points. How about more advanced properties like environmental behaviors? Do materials bioaccumulate? Do they biodigrade? How far can computational material science help?
Yeah, so that's, I mean,
like
you're getting
carbons accumulating in the environment. That's
yeah, absolutely. You're getting at some of the really, I think, kind of cutting edge problems in, material science generally and computational material science in particular. I was just a few weeks ago, I was at a photovoltaic, the IEEE Photovoltaic Specialist Conference. This is something people talk about a lot related to, how do these materials degrade? How can we recycle them? These things. Fundamentally, these challenges come, I showed that plot of the length scales and time scales, right? And if you're asking about a time scale that's much, much longer than what we're able to explicitly resolve in our simulations, that's inherently going to be a challenge, right? You're sort of off the Pareto front of what we know how to do. And so you're then pushing forward both the kind of science and the methods for solving and simulating the science at the same time, which means that there's kind of large uncertainties there. I think that's something that material science broadly is working on, and that certainly Julia has potential to contribute to, especially when it comes to some of that uncertainty quantification. I think AutoDiff and all of these tools are going to be really valuable there. But yeah, I mean, broadly, I think some of those things we know how to answer, at least in a sort of heuristic sense, thinking about the thermodynamics and maybe to the extent that we can quantify kinetics. But it's something that I would say is an open problem in the general sense. There's kind of bespoke solutions for individual contexts, but maybe not generic answers to all of those kinds of questions at this point.
Oh, sorry. You were talking about the integration with LAMPS for molecular dynamics, and I was wondering, do you plan something similar for big quantum chemistry packages like QChem? I think they were also doing something at MolSim at one point. So,
Yeah. So QChem, I don't think anyone has written an interface there, but I mean, if you're just looking at the text-based I/O, or I think the API they offer, I think this shouldn't be too hard. I think somebody's written an experimental integration for Orca, so that would be an example of a Gaussian-based quantum chemistry code. So yeah, there is of course work in this direction because these things are out there and they work. But actually, maybe let me emphasize. So I was talking about like cross-ecosystem integration, and actually the point is that we don't need to integrate with everyone. We only need to integrate with important people. So for example, what I mean is like we need to integrate with sort of other interfaces. So ASA and ASE and IPy, for example, they have integrations with, for example, QChem. So if we integrate with ASE, we're done, right?
I've never used this.
Yeah, so that's basically the idea here, right? So we don't want to like redo all the work that others have done. That's what I meant by ecosystem, cross-ecosystem integration, right? I don't want to replicate that. I want to use that. So that's, yeah.
Yeah, thank you a lot. I wasn't aware of that.
Package that integrates a lot of diverse external tools extremely well is JMP. Have you compared sort of what level challenge they faced in getting a working ecosystem versus what you have to do? I would worry that yours is even more diverse in terms of the tools and the inputs and all this kind of stuff.
Yeah, I worry too. The honest answer is no. Right, so so we definitely wanted to look a little bit into other ecosystems, but to be fair, like it didn't get fully across. But right now, just us, like the few people who are talking to each other, us agreeing on an interface and one way to communicate, that's already a problem. Like it takes a lot of real honest work, and I think we're simply not at the stage where it makes a lot of sense to start looking at these things. But I agree with you that we should do that.
Yeah, and I'll maybe just add briefly, I think that's another place where the funding becomes a challenge, right? Because we kind of have to some extent, focus on the things that we have funding to work on, and we can sort of expand the scope a little bit beyond that. But these much more ambitious kind of interoperability and compatibility projects I think are something that you kind of need a more firm sort of financial support where you can put someone on that as basically their full-time job. And we're not there yet as a community. Hopefully we will be someday.
All right. So thanks again to our awesome afternoon keynote speakers for the first day of JuliaCon. We have a small gift for you both.
Cool.
Thank you, Jorge.
Julia's Vineyard and
Oh,
Chateau
nice.
Julia. Look at that.
Amazing.
Very cool.